Hello everyone, this is Vishwajit Naik from IIT Kharagpur. Today I'm going to review the week 3 lectures. Uh, so it comprises of DIC microscopy, fluorescence microscopy, and the sample preparation techniques. So first let's go through the DIC microscopy. But it's an optical system which uses gradient in the optical paths, or the so-called optical path difference. Here DIC means differential interference contrast microscopy. Interference contrast microscopy, and in the name itself describe this kind of microscopy. It uses the gradient that is formed in the optical path length. And this gradient, what is formed, is seen as a contrast in this microscopy. So what are the principles behind it? So first important point it employs is dual beam interference. The so what it does is like it transforms the local gradient in the optical path length into region of contrast in the object microscope. So whatever changes is happening in the optical path length, these are transformed into the contrast. Whatever changes happening in the optical path length, these are transformed into contrast. And hence in the picture we can see a clear difference in the images that is formed. So next important point explaining the DIC microscopy is that it uses beam shearing interference system. What does this mean? Beam shearing interference system. Here what it does is the reference beam is sheared by a small amount. The reference beam is sheared. That means it is little bit bent like this. When we have a box, a rectangular box, here shearing means if a force is applied on the top of the material, then this deformed like this. This deformation is called shearing. So here the reference beam is sheared by a small amount, and this change in this reference beam, what it determines will happen in the image. So how it produces a different gradient in the optical path length, like it produces a monochromatic cast image. Like how it shows gradient of optical paths, that is this technique produces monochromatic shadow cast image, and because of this reason it is able to create this gradient in the optical path. Now, like, which portion as seen as brighter or darker? What portion of image will look brighter or darker? That depends on what is happening to the optical path difference. If the optical path difference increases in the specimen itself, then the reference direction will look brighter. Optical path difference increases along reference direction, then that portion will appear brighter in the specimen. So similarly in darker case, the optical path difference will decrease. If the optical path difference decreases, then that portion of specimen looks darker. And this is how they create the contrast. How this technique creates contrast. So how can we then control this contrast? Why we can, as we saw, the path difference is the main factor here. So the if we'll make the optical path difference more steeper, then it's possible to increase the contrast of the material. If optical path difference is made steeper, then we can increase the contrast. So, so next, then after explaining the principle behind this DIC microscopy, then we'll discuss about what are the optical system involved and how it is creating the image. So as we have already learned, uh, this is creating image from the phase contrast of the material. So how it is then different from the phase contrast microscopy then? So in the phase contrast microscopy, it takes the difference between the phases of the material, but in this DIC it takes the difference of the phases of the phases, and then it translates into the amplitude. So while explaining the optical system of this material, first this in this DIC microscope, the specimen is sampled by pairs of closely spaced rays, uh, which are generated from the beam splitter. So in this optical system, a beam splitter is there, which divides the incoming beam into a pair of closely spaced rays. And then if any one of the rays from the pair encounters an object where there is change in refractive index or thickness of the medium, then one of the rays from the pair will experience a different path from its paired ray. So this is how a contrast is developed in the material. So if any one of the rays from pair, like from beam splitter we are getting a pair of beams. So those pair of beams, what they are happening, that if they encounter an object where there is either change in refractive index or thickness of the medium, then one of the ray experience a different path than the other. In this way, a contrast difference is created in the image. So how it is different from the phase contrast? In phase contrast microscopy, this is DIC microscopy, the amplitude corresponds directly to optical path difference between specimen ray and reference ray. But here in DIC microscopy, this amplitude corresponds to the derivative of optical path difference and not directly to the path difference, which is the case in phase contrast microscopy. So if we consider this graph, like optical path difference is given, so here we can see there is this positive slope corresponds to high amplitude, and this negative slope corresponds to low amplitude. So here it shows the plot of optical path length across diameter of a phase dense object. So when we see in DIC microscope the derivative of optical path length curve, then we just have to take a differential of what curve this is. So here the change is happening at these two portions. So here other will remain constant, and only where there is change in the slope we'll see a minima or a maxima at those portions only. So this is the difference between phase contrast microscopy and DIC microscopy. So in the optical system, there are certain new things are added with respect to what we have learned in phase microscopy, like the DIC prism, which is otherwise known as Wollaston prism. How it helps, we'll look now. This DIC optical system this comprises of a polarizer, comprises of two polarizers, one polarizer and the analyzer at the other end. Then this new thing called DIC prism, is a condenser here, object is here, and objective is here, another Wollaston prism and analyzer. The light ray is passing through the analyzer, Wollaston prism, then through the objective, passing through the object, and then through the condenser, entering the Wollaston prism, then through the polarizer. This condenser prism acts as a beam splitter. The Wollaston prism, or it's called condenser DIC prism. This acts as a beam splitter, producing two closely spaced parallel beams that traverse the object and are recombined by an objective DIC prism here. So what is this DIC prism or so-called Wollaston prism? These are nothing but beam splitter. They're made up of two wedge-shaped slabs of quartz. Why quartz? As we have already previously read, quartz are bifringent material, and they help in producing two rays, one ordinary ray and an extraordinary ray. So what it does is they split the incident rays. This is a bifringent material. So they split the incoming linearly polarized light into ordinary ray or extraordinary ray. What are these? As I have already read in previous lecture, this ordinary ray and extraordinary ray are nothing but rays which are mutually perpendicular to each other in two different planes. So here two type of Wollaston prisms are used. One is normal conventional Wollaston prism, and another is modified one. And this helps in recombining this pair of ordinary ray and extraordinary rays. So next, how the image is formed in this DIC microscope. Here one incident beam of linearly polarized light first split into ordinary ray or extraordinary ray through condensation prism. Linearly polarized light is split into ordinary ray, extraordinary ray through a condenser DIC prism. So these are focused by condenser lens onto the specimen. This will be focused onto the specimen. So if there is any absence of path difference, then this ordinary ray and extraordinary ray, they will combine by the objective prism, and they will totally be blocked by the analyzer, and we will see nothing. And if there is a path difference, then only we will get any image. So what is happening here? So let's say if our incident ray of linearly polarized light are split by condensation prism into ordinary and extraordinary ray that are passing through the specimen. If they are having both linearly and elliptically polarized waves, then only we will get some result from analyzer. We will get some image in analyzer. Otherwise, whatever is coming from the polarizer, that will be negated by the analyzer. So For example, to consider one example, let's say phase shift given respect to shear axis. So the let's say from the Wollaston prism, the rays are exiting through those, and they form two distinct planar wavefronts that meet in the image plane. So each front shows localized region of phase retardation, which are caused because of different phases those objects will be having. So they will give us a different reconstruction of those ordinary and extraordinary wavefronts in the image plane, which are taken along parallel to the direction of shearing that has happened in the object itself. So in this type of material we can see a dip. This dip represents magnified object diameter. This width represents the magnified object diameter, and this depth represent phase retardation. So after combination and interference, the resultant image may be represented as an amplitude plot, which you can see here. We'll do an amplitude plot. So here we can deduce that the image of the spherical object shows a darker central interference fringe flanked on either side by region of brightness. As you can see, if you have this kind of images, what this is showing is we have a central dark interference, dark central interference, and here brighter at the edges. So this is how we get a contrast in our material. If a background is totally black, then a contrast is seen at the edges. This will be dark, and this will be dark, and this at the edges this will be brighter. This will be dark and this will be dark, and the contrast is created. So this is how an image is formed in DIC microscopy. Then moving on next to fluorescence microscopy. So here also we will explain principles involved. So first and foremost, in fluorescence spectroscopy, what is the physical basis of this? Like uh, it is basically the emission of photons by an atoms or molecules whose electrons are stimulated to a higher excitation state by either radiant energy from an outside source, which will be providing. If let's say we have a ground state, we are providing some energy through outside source, then it will be excited to some states available here. Excited state, then they will relax to give fluorescence. So there are a lot of things happening here. There can be some internal conversion, or there might be inter-system crossing, and then from this is called singlet state. From singlet state, from inter-system crossing, it may go to excited triplet state, and again they may de-excite from this excited triplet state to ground state, and this process is called phosphorescence. And if directly it is de-exciting from the excited singlet state, then it's called fluorescence. So here the fluorescent material should absorb a photon of appropriate wavelength, and after absorption an electron is excited to a higher energy state, and that process is immediate. That the electron in the excited state comes back to the initial ground state, and in the process of energy collapse, the molecule can release absorbed energy as uh, fluorescent photon, and since some energy is lost in the process, the emitted fluorescent photon uh, they exhibit a lower frequency of vibration and a longer wavelength than excitatory photon that was absorbed, and that we can see in different um, uh, figures as well. In fluorescence spectrum, we will see that in absorption spectrum, like if absorbance is like this and the emission is like this, then there will be some shift in the absorbance and emission, and this shift is called Stokes shift. Okay, and this diagram is called uh, Jablonski diagram. Here a series of increasing energy states can be seen, and each energy level is composed of sub energy levels. So there are two categories of excited states here, and they are characterized by different spin states of excited electron, the singlet excited state and the triplet excited state. So here when the energy if the excited electron comes back to the ground state giving up some energy, then as we can see we can get a fluorescence uh, photon if uh, the energy given up as heat, then there is no photon emitted, which is termed as internal conversion. Here the energy is given as heat, and we see no emission of photon, no photon emission. So here the molecules that are capable of this kind of excitation and de-excitation are called fluorescent molecules, and they are also termed as fluorescent dyes or fluorochromes or fluorescent dyes. They show this kind of behavior. So here re-emission of fluorescent light from excited dye molecule occurs over a broad spectrum of longer wavelengths. Even if the excitation is happened with a laser, which are basically monochromatic source, and uh, this happens because electrons occupy excited states for various lengths of time, during which they give up varying energies, for which they give these longer wavelength photons over a spectrum of wavelength. As some energy is lost during the process, the wavelength of the photon which is emitted is usually longer than the wavelength, as I have explained here, and there is a shifting happening which is called Stokes shift. So here the effective separation and detection of excitation and emission wavelength is achieved in this microscopy through proper selection of filters, either to block or pass specific wavelengths, which will help us to access certain region of wavelength, so that we will get our desired result. So what are the basic principle behind this uh, fluorescence microscopy is first, the basic function of fluorescence microscopy is to irradiate the specimen with a desired and specific band of wavelength, and then we separate the weaker emitted fluorescence from the excitation light. So here first irradiate specific band of wavelength, and this can be done using the filters as I have explained. So here the only the emission light reaches detector. uh, if that will happen, then the resulting fluorescent structure are superimposed with high contrast against a very dark background, and then we can get a contrast difference with the background from the sample, and this is how we differentiate the sample from the background. So what are the limit of detection which are here? This is a limit of detection. These are governed by how much the background is darker. So it depends on the darkness of background. So whenever we will choose a sample for this microscopy, then we have to make the background darker as compared to the features we want to study here. And with respect to the background, the excitation light which will be used will be very high, like million times brighter than emitted fluorescence. Whatever photons we will get with respect to that, this will be very high. So what other things are used in this microscopy? One is fluorescence vertical illuminator. So what is this? The this helps in passing uh, this is produced by passing multispectral light from an lamp which will be using as a source, and then we will, with the help of this, we will select a particular wavelength of light. Then the wavelength is passed through the excitation filter that reflects from the surface of a mirror, which is called dichromatic mirror, and then it passes through the objective and we see the light coming through the specimen. Here it gives a specific wavelength of light, and this is produced by arc discharge lamp with the help of selective excitation filter. Then it is passed, the whatever light passed through the excitation filter, this is passed through a dichromatic mirror or a beam splitter. Whatever wavelength of light passes through excitation filter is allowed through a dichromatic mirror or a beam splitter. Then if the specimen is fluorescent, then the emission of light that is gathered by the objective passes through the dichromatic mirror and is filtered by a barrier filter which blocks the unwanted excited wavelength, and we get the eventual light. So a typical fluorescent microscopy diagram looks like this, like a filter cube will be there, where there will be a dichromatic mirror is there. The light, here excite the filter is there. Light is passed through this filter, passes through this mirror. A barrier is there, which helps in getting rid of unwanted excitation wavelength. And here the light passes through the objective and to the object. This dichroic or dichromatic mirror, or otherwise called beam splitter, it is a long pass filter and coated with multiple layers of dielectric materials, and hence the name dichromatic mirror. So this is a gist of fluorescence microscopy, and it is important to note that the fluorescence which is happening is in this microscopy, this is a specimen property. Here the specimen itself produces its own light. Oh. So coming to the next topic, sample preparation technique. Here for different type of materials, different type of techniques are used. So so first of all, like let's say for a metallic specimen is given, first a sampling is done, then a preliminary preparation is done for that, then it is mounted on some substrate, and after that it is fine grinding or polishing is done, and then it is seen under a microscope. So for specimen preparation, first process which is done is sampling. It is basically cutting the specimen which we want to work with from the object. That can either be done through sawing or through using a thin abrasive cutoff wheel with some coolants, that may be water or some cooling oils can be used. Then after sampling, the surface, whatever it is made from the object, it is smoothened. That can be done through fine grinding, polishing. So what are the different things which are used during polishing? Here for fine grinding we can use the sandpaper of different pore sizes. And polishing, what the material used, that can be alumina, magnesia, chromic oxide, or diamond. So another, then we have to mount the sample on any substrate. So another very important thing here is etching. So why this thing is done? Because this helps in revealing the structure of a microstructure which is present in the sample itself. This is very important. So this can help to reveal the dendritic pattern present in the microstructure, or it can be how the material is connected, which is otherwise called segregation, or how the material is deformed at different places. That also we can see using this method. The grain boundaries, which are very common in different processes, we can see, and different phases occurring. Then how much homogeneous our sample is, and different kind of interfaces we can see if we have different kind of materials or heterostructures. Then different kind of heat affected zones in case of ceramic materials or polymer hard and polymer materials. This kind of things we can see using this process. And what are the technique used for this etching? Those are swabbing, immersion, or electrolytic. Like swabbing means, like, as we know from the term itself, we use ear swabs. Like we with the help of some materials, we will uh, swab the surface or the clean the surface of the material. Immersion, we will dip our material into certain kind of chemicals or etchants that will help in removing some of the top surface, so that we will get the microstructure. And in electrolytic process, we will the help of current, we can remove the top surface, and we can see the microstructure. These two, swabbing and immersion, these are manual process, but whereas the electrolytic process is not. So this etching process, as I have already explained, this helps in highlighting and identifying the microstructural features or different phases present in our material. Uh, what type of thing we can easily see? Only the non-metallic inclusions or porosities or cracks can be easily seen from by etching. So this what this etching process is done, like it is based on the rate difference in uh, so it is based on rate difference in chemical attack, whatever chemical or etchant will be using. So that how it attacks depends upon the chemical composition, energy content, and the grain orientation of our sample. So since the grain boundaries are attacked at a greater rate than the proper grain due to higher energy content of grain boundaries, so we can see easily a contrast difference across the grains and the background in our sample. So in addition to that, the presence of chemical different phases, that the different phases also have different chemical attack. Different phases have different rate of chemical attack, and this changes in a rate of chemical attack, they produces a variation both in angle and depth of certain portion of the surface, and hence it creates the contrast difference with respect to the background. So when the light is reflected in different amounts depending on the angle and depression of the portion of the surfaces, they result in light and dark regions, and in this way we get the crystal microstructure of our specimen. These etchants they can be dilute acids or alkalis in water or alcohol or some other solvent, and when they come in contact with the specimen surface, because of different rate of attack of various phases and orientation, they etch out differently the surfaces. So here we can see some of the material compositions and their application and the procedure with which these etchants are used. For iron and steel, uh, we use 1/5 part of nitric acid with 100 part of 1 to 5 parts of nitric acid used with 100 parts of alcohol, and 1 part ammonium hydroxide, 1 part with 3% hydrogen peroxide, and 1 part water. And this is immerse or swab, like we can either immerse the iron or steel in this etchant, or we can take this uh, etchant in a swab and we can rub it on our specimen, and we can etch out the top surface. For copper and brass, mm, we take this 5 gram ferric chloride, 10 ml hydrochloric acid, 100 ml water, 5 to 10 gram of ammonium persulfate, 1 ml hydrofluoric acid with 99 ml water, and this can either be done through swab, immerse. These are the different etchants used for copper and brass. For aluminium, This two type of etchants can be used: 10 gram of sodium hydroxide and 100 ml of water. This can be used by immerse process, and 10 gram oxalic acid and 100 ml water. This can be used in electrical process. For stainless steel, 5 ml of sulfuric acid with 100 ml of water can be taken, and this etching can be done through electrolytic process. Now coming to the problems. So with etching, we have different kind of uh, uh, processes involved. One called macro etching. The process is utilized to reflect the heterogeneity exist in metals and alloy. So with this, in addition to this, different structural defects left from the solidification or mechanical processes also they can uh, give the information about this also, different structural defects. Then heterogenesis resulted from carbonation or decarbonation processes, and also the physical defects, the cracks, pores, all this can be seen easily. And physical, all this process can be noticed by macro etching process. And also other things like welding, heat treatment, and quenching effects, what are the cracks and regions which are being affected, those can also be seen by using this macro etching process. So in steel industry, this process is widely used for quality control. Uh, how in steel industry, what are seen in steel industry? The ingot which is formed, what is the structure of it, the segregation, inclusion, presence are all detected by using this macro etching process. Then etching of a sample having multi-phase structure. So the etching mechanism of multi-phase structure has electrochemical properties in those. So the once the sample is reacted with the reactive potential difference, react with the reactant, the potential difference between different phases are formed. The phase having higher electropositive potential behaves like a positive electrode and start to dissolve during etching, and the other phase behaves like a negative electrode and will remain without any change. The concentration of etching solution and the process duration have to be optimized to get the desired result. So during the etching, the dissolution of positively induced phase will result in a crater formation. So during the microscopic analysis, the light cannot reflect through this crater, and hence it forms darker region, and where light will reflect a lot from the negatively induced phase, and that will seen as a brighter region. So in this way, a contrast difference is created. The next is etching of pure materials. Etching of pure, beg your pardon, and one phase structured materials. Here the etching of homogeneous one phase structure material is different than that of multi-phase structure samples. So here in this case, the Etching mechanism is based on electropositive process. Since the potential difference between the matrix material and bulk material or the grain boundaries are very small and very difficult to detect. So it is uh, aimed to notice the differentiation in the grain depending on the dissolution rate. Next is reactives used in etching. So the reactives used in etching are basically formed from solvents. Uh, they, they, and these solvents can be water or alcohol or glycerin or any mixture of organic and inorganic acid. So the this reactivity and the effect of the reactives that depend on the hydrogen ion concentration. They depend on hydrogen ion concentration, hydroxyl ion concentration, and the black beam effect. So each materials needs proper reactive. The reactive used in steel and hammered iron have different component than what we will see in let's say bronze or brass. So the last etching process is electrolytic etching. So this etching is done in an electrolysis cell, and this process is used for electrolytic polishing of stainless steel. So here the solution used in electrolytic polishing, they can be either acidic or basic, and here that sam samples which are used in the anode, the DC current is applied to this anode, and the etching process is controlled by varying the applied potential value and the process duration. So these are some of the etching methods which are used to do the pre-processing of material, and after that we can see that this in under electron microscope. So first problem, like first optical tube length is given as 150 mm and the distance of distinct vision is given as 100 mm, and focal length of objective lens is given as 150 mm and focal length of eyepiece is given as 10 mm. So what is the total magnification? The total magnification is given as the product of magnification of objective with the magnification of eyepiece, and this is given as the product of tube length with the distinct vision distance divided by the focal length of the objective and focal length of eyepiece. And this T is already given here, 150 mm, and D is given 100, and focal length of objective 150 and focal length of eyepiece is 10. So we can calculate this, and the magnification is 5. We can find as 10x. Refractive index for sodium line is given as 589.3 nanometer, and hydrogen F line is given as 486.1 nanometer. Hydrogen C line is given as 656.3 nanometer. The relative reciprocal dispersion is given as refractive index of sodium D line -1 divided by refractive index of hydrogen F line minus refractive index of hydrogen C line, and we can put the values and we will get the result. We call relative reciprocal dispersion. The refractive index of objective lens is given, and the condenser lens refractive index and semi-apex angle of 10 degree. Wavelength of light used is 250 nanometer. Will they give optimum performance in bright field imaging? So to know whether it will give optimum performance or not, for that, what was the condition? For optimum performance of microscope, our numerical aperture of objective should be equal to the numerical aperture of condenser. So we can calculate the numerical aperture of condenser and objective. For objective, it is given as sin alpha, which is 50.5 into sin 10 degree, and numerical aperture of condenser is sin alpha. So from this we can easily see they are different. So this will not give us the optimum performance in the bright field imaging. Now to calculate the resolving power is given as 0.5 lambda by numerical aperture of objective plus numerical aperture of condenser. Here we can calculate numerical aperture of objective as 24.9 sin 10, which is 4.324, and this will get from here we can put the values here and we can calculate the resolving power. The wavelength of polarized light given as 174 nanometer. The thickness of medium is 0.2 millimeter. Refractive index of ordinary ray is 2.5 nanometer and refractive index of extraordinary ray is 3.7 nanometer. Calculate the retardation and phase shift for retardation. So relative retardation is given as difference of refractive index of extraordinary ray and ordinary ray times the thickness of medium. Here,
hello, sir. Hello.
Yes.
Sir, screen is not visible.
Screen is not visible.
Uh,
Now or since a long time?
Sir, it is from long time, but I have not found anything in screen.
Uh, okay. Can you refresh, like, or check your internet connection or disconnect and connect again?
Okay, sir, I will try.
So the refractive index of uh, extraordinary ray is 3.7 and refractive index of ordinary ray is 2.5. Yeah, thank you for confirming. So, and the thickness of medium is given as 0.2 millimeter. From we can calculate the relative retardation as and the phase shift is given as 2 pi delta by lambda terms of radian. Here you can plug in all the values. Delta from here, lambda is 174 nanometer. We can convert it to a SI unit and calculate the result here. Here if we say 3.7 minus 2.5 into 0.2 10 to the minus 3 and this one nanometer 10 to the minus 9, we can find this as minus 12 and here we'll put it I can calculate what will the result. So what's the relationship between resolution limit of red and blue light in the visible spectrum? So the resolution is given as lambda by 2Na. So if the wavelength of red light is given as 700 nanometer and the wavelength of blue light is given as 475 nanometer, and we assume that our angle and refractive index are same for both the cases for red and blue light, then the numerical aperture of red would be equal to the numerical aperture of the blue. From there we can say, can equate here the numerical aperture is equal to lambda by 2d. So the resolution of red with respect to the resolution of blue can be given by only the wavelength of red and wavelength of blue, which is 700 by 475. So we can say the resolution of red is 1.47 times the resolution of blue light. So for same values of numerical aperture, magnification in optical microscope, what the relationship between brightness in trans illuminator and an epi illuminator? Trans illuminator is basically in transmission microscopy and epi is reflected microscopy. So the brightness for trans illuminator is given as numerical aperture by magnification square, and for Epi, it is given as numerical aperture to the 4 by magnificent square. So if you take the ratio of brightness of trans illuminator and epi illuminator, it will be given as 1 by nh square. So for any given standard value, numerical aperture, as we know, can be given as mu sin alpha. For any given standard value of mu and alpha, we can calculate the numerical aperture, and then we can compare the brightness of trans and epi illuminator. Calculate the depth of field. For wavelength lambda 600 nanometers, refractive index of 1.5 and angle of 42. Establish the effect of numerical aperture on depth of field and resolution. So what happens when we change the numerical aperture here? So the depth of field is given as mu lambda by numerical aperture square, but the resolution is given as lambda by 2na. Here mu is given as 1.5, lambda 600, and numerical aperture will be mu sin alpha, so which will be 1.5 sin 42. This will be around 893 nanometer, and here lambda 600 by 2 times 1.5 sin 42. You can calculate this as 298 nanometer. So here, how change in numerical aperture is affecting the depth of field and resolution. Now when numerical aperture is increases, here the depth of field is becoming smaller, and we can say it is worsening, it is getting bad. And but the numerical aperture is increasing, the resolution is getting smaller, and we can say it is getting better. This is the relationship between numerical aperture, depth of field, and resolution. In phase contrast microscopy, two specimens are inspected. First specimen having refractive index 1.83, and second specimen has a refractive index 1.58, and we have air with refractive index of 1.33. For the same thickness of both the specimen, 0.5 micrometer, which specimen will have better contrast? So to understand this, we have to know what are the correlation of contrast with different parameters. So we have to go down to the refractive index one. So first, the contrast is directly proportional to difference in intensity, and this difference in intensity is proportional to the phase difference. And this phase difference is directly proportional to the path difference. So for specimen 1, we have N1 and 2 value 1.83, and N2, which is taken as air, 1.33, and thickness for the medium is 0.5 micrometer, and for specimen 2 the N1 changes to 1.58 and thickness remains the same. From here we can calculate the path difference. How will calculate that? The optical path difference is given as, in specimen 1 it will be N1 minus N2 times T, which will be 1.83 minus 1.33 times 0.5, which will be around 0.25 micrometer, and for specimen 2 it will be around 0.125 microns. So from here we can see the optical path difference of 1 is greater than the optical path difference of 2. So as we know, the contrast is directly proportional to the optical path difference. So we can say contrast of specimen 1 is better than contrast of specimen 2. Than contrast of specimen 2. So for compound optical microscope, prove the magnification as this, where f1 is the focal length of objective and f2 is the focal length of 1 corresponding to objective and 2 corresponds to the eyepiece. u1 is the distance of object from objective and v1 is the distance of image from the eyepiece. So we can say the total magnification is given as magnification of objective times the magnification of eyepiece, and from our lens formula we have magnification as v by u. So for objective lens 1 by f1 is equal to 1 by u1 plus 1 by v1. So we can get the distance of image eyepiece from here as one by f1 minus 1 by u1. So from here we can say the distance of image from eyepiece is given as u1 f1 by u1 minus f1. Similarly, from here we can say the magnification of objective is given as f1 u1 by u1 minus f1 by u1. So f1 by u1 minus f1. So for eyepiece, magnification of eyepiece is given by v by u, where it is v2 by u2. From here 1 by f2 equals 1 by v2 plus 1 by u2. We can get the value of u2 as v2 f2 v2 by v2 minus f2, and this we will plug here to get v2 by F2 V2 by V2 minus F2. So it gives you V2 minus F2 by F2. So the total magnification be given as the product of optical magnification times the eyepiece magnification, which be given as U on F1 by U1 minus F1 times V2 minus F2 by F2, which has the desired result. So crystal of different orientation are etched at different rates. This result in contrast change due to ledges formed at the grain boundaries, change in crystal orientation, elongation of grains, or resolution change. Here, as we etch out the sample, the contrast changes because of the ledges which are getting at the grain boundaries, and difference because of that there is a difference we get at the uh, soft background and the material background and grain boundaries. So first option. So here, what is the useful magnification of a microscope? If the numerical aperture of a objective lens is 0.9, so when we have a numerical aperture of 0.9, then our magnification, total magnification, we can say, like here total magnifications are given. Okay, so we can take the product of those and we can predict the numerical aperture, and the total product shouldn't increase the product of the two values here. So for numerical aperture 0.9, it should be higher than 500, higher the magnification should be higher than 500 and lower than 1000, then only we'll get the desired result, and this is given by the second option, 500 to 1000. If let's say we have 250 to 500, then the objective lens is having magnification less than 500, and the product will not give us, the product of magnification will not give us the desired result of 0.9 numerical aperture. And if we'll consider, and all are similarly, like this doesn't have the lower limit, this doesn't have the upper limit 450 to 900, so accordingly you can eliminate other options and only option remains is 500 and 1000 here. Three main etching technique employed in specimen preparation of optical microscope: swab, immersion, and electrolytic, which are done manually. Swab and immersion are done manually. So I have told like these processes. Swabbing means uh, we uh, etch out the top surface by using a swabber, and this immersion, we will dip the specimen in the etchant and it will remove the top layer. So these two are manual processes, so option will be this one and two. Fluorescence microscopy, the dichroic mirror acts as a band pass filter. No, it acts as a statement is false because it acts as a long pass filter, not as a band pass filter. In different DIC microscope, the relation between amplitude and optical path difference is derivative, as the name suggests, differential. Which of the following component is only seen in DIC microscope and not in phase contrast microscope? In the image, we do see iridescent faceplate is used in phase contrast, obviously, and angular ring is seen in the image part. So the extra term which remains is Wollaston prism, which helps in the dividing this polarized light, linearly polarized light, into ordinary and extraordinary ray. So that's why this Wollaston prism is used in DIC microscope. In DIC microscope, which of the following factors affects image contrast? Both the refractive index and the thickness of the material affects the contrast of the image. The bifurcant is used to make the DIC prism, as we have previously seen, like quartz is the material which is used. Which of the following statement concerning bifurcant material is not correct? It is optically anisotropic. It is correct. It is exhibited by non-cubic crystals. Correct. When light beam passes through the bifurcant material, they go through double double diffraction. So these three statements are correct, but it is that which of the following statement is not correct. So quartz is a non bifringent material is not correct, because quartz is a bifringent material. What is the DIC prism's function? DIC prism, as I have already told, it splits the linearly polarized light into ordinary and extraordinary ray. It acts as a polarizer, no, splitting the polarized light into two components, correct? Splitting the polarized light into multiple components, no, there are only two components present, ordinary ray and extraordinary ray. Converging the polarized light into a single component, no. So the answer is splitting the polarized light into two components. So what are the correct statement here? In DIC, amplitude correspond to derivative of optical path difference. This is the first statement is itself correct. In phase contrast, amplitude correspond to the derivative of optical. This is incorrect, because amplitude correspond to the it correspond directly to the optical path difference. The phase contrast utilizes only phase shift of illuminated image beam for image. No, it's not only the phase shift, it also takes into account the diffraction. Here from the last option it is written doesn't require diffraction of the illuminated beam. It is not correct. It does require diffraction for phase contrast to happen. Which of the following information can qualitatively obtained from an optical micrograph? Texture, yes, as we have already seen in the sample preparation process. What are the different things which we get? Texture, we do get residual stress, grain orientation, distribution. All of them we can get all the information from optical micrograph. So answer will be none of the above. So how to define etching? Coloring of the sample, no. Coarse polishing by emery sheets. Coarse polishing. Oh, it's a polishing process.
Lower
It's different from
magnification
etching.
imaging is
The
done.
preferential attacking of regions by chemicals. This is the correct option. Using fine ceramic powder polish. This is again example of polishing. This is also example of polishing. So this is the only option for etching. For uh,
Etching,
uh,
higher magnification
lower
imaging is
magnification
done.
imaging, this deep etching is preferred. Actually, in the lecture itself, sir has explained uh, for deep etching.
Now, moving on to the next question. In fluorescence microscopy, uh, we normally use n- near violet end of visible spectrum as a source. Going to the next question. Epoxy and hardener uh, comes mostly under cold mounting, whereas bakelite comes under hard mounting because in cold mounting it is recommended for the mounting of individual or series samples, the fragile and sensitive to heat, whereas in hot mounting is recommended to achieve a high quality mounts where it offers a greater hardness and allows to control the mounting diameter.